Welcome to another GC Basic tutorial for the 16F175 chip family. This is part 9 of the series of tutorials for this particular chip family. And let's get started. So, part 9, timers and timer interrupts. So we're going to look at a number of different ways of using the timers and how we set them up nice and easy for this particular chip. Like and subscribe, as always. If you do watch, just subscribe. Just subscribe and like it. So number 9, we've done sort of set the board up. We've set the LEDs. We can rotate the LEDs, and we can use switches and inputs. And it's really good. It's quite simple. And what we're going to do is use timer 0. I'm assumed that you have got all the software installed, that you've tested you can program this particular chip. You've got LEDs, etc., all connected up, because that's what we're going to be using. Now the hardware I am using, let me show you mine. I am using this. Let me have a look. This is the board. I got quite a few of these. No, I got more. I got more. Yeah, I got 10. Okay. Now why have I got 10 of these? Because I'm constantly working on GC Basic, so I need lots of boards. Okay. All right. And I have them set up with different configurations. So this configuration has a 175xx mounted here. It has 4 LEDs mounted here with flying leads or via suitable resistors. But also, I've hooked up my Gabtronics oscilloscope, and we're going to see that working shortly. So I've hooked up my oscilloscope input to one of the LEDs. So when it pulses, we are going to see the result. But we're not only going to see the result on here, we're going to see it on the computer. This big lead here, that's connected to my PICkit2. And this is a PICkit2. It's PICkit Plus. There you go. Look. Nice little programmer. Works really well. Okay, let's just set that all back up. There we go. Now, this is the logical layout of the hardware. Essentially what we're going to do is I'll bring my pen up. We're going to activate these 4 LEDs, 1, 2, 3, and 4, and I'm sampling one of them with the oscilloscope. They're set as, it says digital input, but it really shouldn't be digital input. These are digital signals, and I've just laid out where the LEDs are. Now, let's do a primer on the timers, because it's important that we understand how they operate. A timer generates accurate delays. Up to now, we've been using like the wait command, which actually uses the internal oscillator, and it's what's called blocking. It actually counts the number of cycles it needs to go through to meet the time that you used or demanded. Now, a microcontroller can also generate loops in the background, where those timers or counters can be scaled. And then they can be scaled using a thing called a Prescaler and Postscaler in this particular chip. But it's just a binary counter. It just starts at 0 and counts upwards. And once it goes over the 0, once it goes back to 0, it generates an overflow. It's called a flag. And if you have the interrupt enabled, it will do something. You can send it somewhere. And we're going to look at all of that. Now, to make it all work in GC Basics, very simple. You initialize the timer, init 0. I'll bring up my pen. You say init the timer, and there's quite a few timers, so it's init timer. We're using 0, so it's init timer 0. You tell it where the oscillator is. So the first parameter is oscillator. Well, that's weird, but it's not really, because you need to tell it whether it's internal or external. I'll just take that away. And then we tell it what the prescaler is. We tell it the clock source, and then we tell it the postscaler. We start the timer with the start timer command, and then we can set the timer to a value. And set timer is, you can say set timer 1, 2, 3. We're focusing on 0, and you give it a value. And it's either a 16-bit number or an 8-bit number, and that will become very obvious. Now we supply a calculator in a spreadsheet, which you can see on the top right hand side, but there's many ways of calculating the delays. We'll look at that very shortly. But we should look at this timer block diagram because it helps you understand the construct inside of these little microcontrollers. So on the left hand side, bring my pen up, we've got a series of clock sources, and we are going to use this one here. We're using the oscillator divided by 4. And then we have a thing called the Prescaler, which is here. We have a Postscaler, which is here. And then when it tracks over to 0, we have an interrupt flag called T01F. These are the key things that we need to be considering. One thing that was in that diagram was also a little flag, and I'll just show you where it is in going back a slide, is here. Bring up my pen again, is right here. T016BIT. That will tell the timer whether to use an 8-bit number or a 16-bit number. So we're going to use a 16-bit number today and then an 8-bit number just to show you the differences. And what happens is if you set that bit to 0, it uses an 8-bit timer. And if you set it to 1, that 1 bit in all those bits in the microcontroller, it says 16-bit. So if it's set to 0, it goes one way. And if it's 16, it does it another way. So we have to tell it to set this bit. And so we're going to instruct our microcontroller to do one or the other. And we'll see that operating. So let's have a look at how all that puts together. So you can generate very accurate time delays and extremely long delays. And when those roll over to 0, it sets the overflow flag. So let's have a look what happens. So as in that diagram that we saw from the data sheet, you think of it like this, is that you've got an oscillator or external clocks, and you can select those. You just select them. And we've selected the internal oscillator. And it generates a signal. Whatever that signal is, you can apply a prescaler to it. And that prescaler will increase its duty or make the duty larger. So you can take very fast clock signals and make it larger. You can postscale it. So you can take that signal and make that signal even longer. These are dependent upon this 8-bit number or the 16-bit number when it rolls over, but we'll see the signals. And then if we've got the timer enabled, it starts counting. And it goes from 0, so it goes 1, right the way through 0, 2, 3, 4, 5, 6, and then it goes B1, then it goes B2, and then it goes B3, and then load of other numbers. These are all hexadecimal numbers. But when it gets to FE, which is 254, 255, it's counting away at the frequency defined by these original clock signals and the prescaler and postscaler. And eventually the counter will go back to 0 because it rolls over. And at that point, you'll get an overflow. And the overflow flag can be tested. It's a little bit. We test it. It's either 0 or 1. We clear it, 0 or 1. So we know when it happened. And if you have the interrupt enabled, that's another little flag, you'll get an interrupt signal. And the the microcontroller will then go and handle that interrupt. And we're going to see all that working. So what we're going to do is in the reverse order here. We're going to do 16-bit, then an 8-bit, then a timer overflow. We'll look at some code. So let me shut that down. Don't need that. Oh, we'll need that later. Right. Press Windows, GCStudio, GCS. That's all I type, and open it. It opens it up. This is a bit of a zoom. I'm going to take the 16F175 chip range demonstrations in that folder. It opens up the IDE. Control B, or open up the Explorer at the top left-hand side. I am going to take a file called 110, rotate the LEDs using a 16-bit timer. I'm going to also load in the 8-bit timer, and I'm also going to use the timer overflow. So I have told you the three that I've loaded. So that's 110, 120, 130. I didn't load them because I didn't double click them. Double click, double click, double click, because I only clicked on them. Okay, let's go into the 110. Rotate the LEDs uses a 16-bit timer. Let's look at the document. Anything in green is documentation. I asked Grok for the parameters. Grok is an AI engine and you can do the same. So we'll explain that. I have set the frequency here to 16 megahertz. Up to now we've not used that, but comma 16. I did explain it earlier on, but I'm just to give you an idea. These are the constants that have been set up for the hardware, for the LEDs. So the LEDs are outputs. And then this is the same code essentially to rotate the LEDs, but we're not using a wait command. We are going to check a flag, whether it's overflowed or not. I'm going to say, right, use the 16-bit value. Why do I use a 16-bit value over an 8-bit value? The answer is very simple, is that the period is much longer. Greater time periods can be programmed in by using a 16-bit value. The 8-bit value is actually quite, even with the prescalers and postscalers, the range is not that great. So, but we'll look at how we do it. So I'm just going to define this constant, and that just tells the compiler to use a 16-bit timer for timer 0. Hence it's called TMR0 16-bit. It will set the bit automatically. Now I've done the calculations, and I should really show you those calculations, but you can calculate these values easily. But essentially what we're going to do is I'm going to initialize the timer, and I say I'm using the internal oscillator. If it was external, I would type EXT. And I'm going to have a prescaler of 128 and a postscaler of 1. And that gives me a specific range. And I'm telling it that I'm going to use it actually divides everything by 4, so we put a constant in here just to say what that is. I then set the timer to set the timer 0 to my value, which is I've calculated this value of 3036, and then I start my timer. And now the timer's running. So what do? I'm going to test a flag. And the only thing I'm going to do in here, which is different from previous, is I'm going to loop around, rotating the LEDs with this syntax here. I'm going to check a bit, and I'm going to say, has the timer 0 interrupt flag been set? Has it rolled over to 0? Has the overflow happened? Well, you'd have to go through the data sheet and figure this all out, wouldn't you? That particular bit. No, you don't. Because if you go function key F4, typing PIC and select PICInfo, it will take you into the PICInfo, and I've got my chip selected. I will zoom in. In here, there's a tab called interrupts. Click on that, cursor down, and it's got timer 0, and there is only one interrupt available in here. That's called timer 0 overflow, and the flag is called, the event flag is TMR01F, IF. Because look, it says at the top, what's the interrupt name, the enable bit, and the event bit. So I'm just looking at the event bit in here. I don't have to go hunting through the data sheet. It tells me here. And that's exactly what's in our code. Wait while TMR0 IF equals 0. So that means it has not been set. The moment it has been set, we clear it because that's good practice. And then it rotates the LEDs, and then we reset the timer back to our value. So every 1 second, it will do it. So I've calculated the values. Let me just zoom out for you. I've calculated the value of 3036, I put that in a constant because I want to reuse it, and I set a prescaler of 128 and a postscaler of 1. Let's see what happens. Now, what I've got is my little oscilloscope. I will start that up in a minute. So I'm going to come into here and I'm going to press function key F5, and it will then compile the program in a couple of seconds. It will then push it out to the PIC kit. Job done. It's going to start flashing our 4 LEDs. 1, 2, 3, 4. And it's rotating it every 1 second. But how do I know that? Well, I know that because I can show you in the Gabtronics, GAB. Gabtronics is my favorite oscillator. Just going to connect to my oscillator. You can see that I've got it on the screen. Connect. Now, it says not connected. Vase is not connected. Oh, it's powered off. So I'm just going to push the button. There we go. Look. Connect. And I will explain what's going on. So, what we've got is the oscilloscope showing us every time that the blue LED goes high, the oscilloscope will give us that result. And if we actually zoom in, I'll bring it up like this lot so that you can see it in this big screen here. Look, the division in here is every 2 seconds. So if I look at the divisions, I've got 1, 2 divisions. That means every 4 seconds. But I set it to 1 second. Of course, it's every 4th LED. Every time the 4th LED comes up. So we now know we've got 1 second. And we can play with the postscaler, prescalers, and you can do that calculations. I'm not going to show you the details on how to do that. I'm showing you how you put the syntax in. Relatively simple. Recap, set the bit, init the timer, set the timer, start the timer, and then you can use the bits that associated with the timer in terms of the events, which it was in this particular case TMR0IF. So how do you do an 8-bit timer? Remember, the 8-bit timer, the range on the period isn't that great. So if I just bring up example 120, and I'm just going to program it, and we'll see that things are pretty similar. Okay, I'll put the it looks the same. Now there was some jitter on that line as it programmed it, hence it's got on the oscilloscope, it's got the jitter. Now, so what's different? Well, there is no 16-bit constant. We do the same init 0. We use different prescalers and postscalers. Why? Because I'm trying to extend this to make a 10 millisecond. The previous one was 1 second. This is 10 milliseconds because the range, the period cannot be that great. I've set the value to 9C, then I set my timer and start the timer. So I've got a signal coming up every 10 milliseconds. But I want 1 second. So what I have to do inside of my program is I'm going to count the number of times I see this event. So I go into my program, I say wait whilst the timer is equal to 0. I clear the flag, I increment my timer counter by 1, and if it's equal to 100, that should be 99. That's right, that should be 90, because if I reset it to 0 in a bit, there you go. This might be 10 milliseconds out, might be. Anyway, when we get to 100, then we're going to rotate the LEDs, and that's what it's doing. So if I look at the oscilloscope very carefully, I think that's 10 milliseconds too great. It's actually, that should be less. If timer count is greater than 99, yeah, it's equal to 99. F5, hit it. Because we've got 0. So now I'm just reprogramming it. Job done. So we've seen an 8-bit timer and a 16-bit timer, and the only difference is that you use an 8-bit number when you're using an 8-bit timer, but also you don't set that bit, the constant timer 0, bit 16. All this is in the help, by the way. And now we're back to 1 second. Let's look at 130. I'm going to program it. We'll see the results on the oscilloscope, and we can see it visually. It looks no different. It's doing it every second. It's changing the LED. But how's it doing this? Because I'm using a 16-bit timer, because it says it here. I'm looking at example 130. I'm setting the same Postscaler and Prescaler as I was in the previous 16-bit value. I'm setting my value to I'm setting the timer to the same value, but then I've introduced on interrupt. On interrupt, timer 0 overflow. That's an English thing. Call blink. Call blink, and I've got a subroutine called blink. I start the timer. Well, this is different. So every time the interrupt, I'm enabling the interrupt. The on interrupt command here will set up all the handlers for you. It will automatically handle the interrupt as it comes in. It will check it's the timer overflow. It will cache any variables, system variables. It will then call the routine, and then it will restore everything back. So it has a lot more richness to it that you don't need to worry about. And then it will call blink. And where did I get timer overflow from? I got it from PICInfo. That's the constant theme that I can use. So what happens in in my little routine called blink? Well, I set a variable. I set a variable called timeout equals 1. By setting timeout equals 1, then in my main program, I can actually test for that. So in here, I just say if timeout equals 1, then go and do the handler, rotate things. And at the end of that, I just set it to 0, just before I reset the timer. So what it does, the program every 1 second will come to blink. It will set the timeout equals 1, and magic will happen in the main program. I just popped away and had to answer the front door. So I'm back now. So where were we? The logic here is all handled within the compiler. So the compiler will handle the interrupt with this on interrupt. And as I said in the PICInfo, these are all the interrupts you can set. So it carries through from I'll zoom in for you. It carries from the ADCs right the way through to 0 crossing detect. Same process, which would be to set the on interrupt, call something and go and handle it. Keep your routines short. That's a general practice, nothing to do with GC Basic. Okay, back to PowerPoint because I'm winding down. So next we'll be looking at EEPROMs, showing values on the serial terminal, and some more constant insights I'm going to give you. Okay, enjoy.